Very good afternoon, everybody here. Thanks for your attention and come here to attend my sharing session. And very fortunately, this microphone is just nice for me. The height is just nice. I'm going to today. What I'm going to share is about our experience for the last 2 years when we worked on ammonia bunkering and safety simulations from MESD. So what you are going to hear today is more like from a researcher and a technical point of view. But I believe this kind of sharing on the fundamentals of ammonia bunkering and the dispersion study will be very beneficial to all stakeholders here. So this is roughly my agenda for the short presentation. I won't be focusing on ammonia use as a marine fuel or as a green alternative fuel because it has been mentioned so many times. I believe a lot of people has been very well convinced that ammonia has a good potential to be the next generation marine fuel. And as you can see from this, formula here, ammonia is actually free from carbon. So theoretically, you are able to achieve an ammonia energy-powered future without carbon being involved. All right, let's start from some very fundamentals about this famous chart when ammonia was used for refrigerant R717. And this pressure enthalpy chart actually gives you almost everything you need if you do ammonia bunkering, transfer, and boil-off gas management on board or on land installations. I don't have to explain this in very much detail, but do bear in mind that what we are talking about ammonia transfer at different physical state is actually following this line, saturated liquid line. So if you want to use a more professional term for ammonia, we always call it saturated liquid, regardless of what pressure it is being stored at. These are hypothetical process only to demonstrate how do you do ammonia bunkering, whether it is stored as refrigerated liquid or semi-refrigerated liquid or non-refrigerated liquid. So theoretically, you can transfer and bunker ammonia at all possible physical states, as long as they are kept as saturated liquid. Okay. I'm sure this slide has been flashed many times. Everybody knows ammonia is toxic, but it can be managed. I believe, including myself here, many of you may have already handled ammonia in different quantities. First of all, ammonia has a very strong pungent smell. I have handled this numerous times in my chemistry lab. I know the smell. I know my nose is very sensitive. Unfortunately, human nose may be as good as, or even better than most chemical sensors in terms of detecting ammonia. So at low concentration, we can detect it. And of course, you need some numbers to take a reference, which I refer here is AGL level from US EPA at different levels, starting from 30 ppm, around 200 ppm, all the way to thousands of ppms. And of course, exposure time also play an important role. The concentration plus the exposure will give you the consequence and impact to sensitive receptors of ammonia. And this is the level we are referring to for our safety study to create a safety zone and a safety distance. Here are some, just a quick snapshot of different ammonia leakage examples happened in the past 10 to 20 years. So ammonia is toxic. It can cause problem if you are not careful enough, but the summary is mostly from land-based installations. For maritime installation, the main accident currently come from fishing boats when they use ammonia as refrigerant to store the seafood at low temperature. But there is one case recently in 2014 where an LPG carrier has a problem with ammonia in Houston. And this is an example of how ammonia leaks, how it works. On land base, you can see ammonia, maybe contrary to most what of you thought, ammonia is actually a heavier gas at the initial stage of release. Gradually, it gains heat from the surrounding and becomes a light gas. And eventually, it will be diluted by air and disappear. And this is what happened 2 years ago when an ammonia carrier leaks about 1,000 kg of ammonia onto the seawater. What you can see is actually a cloud, and this cloud clings to the sea surface for quite some time before it has much more buoyancy and disappears. Of course, some science and technology to understand this phenomenon. As you can see, when ammonia is spilled onto the seawater, what happened is that ammonia initially leaked as a liquid, as big droplets. And once the droplets falls on the sea surface, it becomes a smaller droplet. If the flow is quite high enough, you will have an ammonia pool. And this pool can cool down the seawater surface to form an ice layer in certain cases. So on top of this layer, the pool will boil very violently and give you a dense cloud of ammonia. And this dense cloud, over time, will lose some momentum due to the dilution and heating effect from surroundings. Eventually, it becomes harmless. So this is what happens if you don't do any mitigation. So Mother Nature will take care of it at a cost. So if you zoom out and look at the big picture of ammonia ship-to-ship bunkering, you have to consider every single step after it is released to the seawater. And of course, I don't have to go through the details, but the far-field simulation software we are using, FAST here, can give you a lot of meaningful results. Of course, before you can do a validation or do an experiment to validate the findings. And this is a sensitivity analysis of ammonia leak if you change the operational parameters, the weather parameters. And we recently published one scientific paper on Journal of Hazardous Materials. Later, I will show you the download link. You can take some time and read the paper. You will get a lot of insight. This is just a case study, hypothetical case study. We released up to 17 tons of anhydrous liquid ammonia into the seawater during a ship-to-ship bunkering operation. And all results are generated by FAST software. As you can see here, there will be a mass distribution that tells you how much ammonia is flashed as vapor, how much goes into the sea and fully dissolved. So based on this, we can generate a lethality footprint in Singapore. So we are using Singapore weather and environmental conditions. But in this case, we are using lethality footprint, which combines the ammonia concentration and exposure time. So you have a rough idea at such a big scale release, what kind of a safety zone do you require? And of course, mitigation is very important in case of a release. And every single step counts, in my opinion, because you have to understand each step of ammonia release and dispersion. And of course, accordingly, you can develop ammonia mitigation solutions and technologies on top of this. This is a summary of existing practice to mitigate ammonia vapor for land-based facilities and release. It's a common sense, right? Everybody is using water as an absorbent or create a physical barrier to stop ammonia. But in the future, when it comes to very huge scale release, what technology are you going to use and develop? So it still remains a question mark to MESD. So in the next 2 years, we are going to develop something new or something meaningful to address large quantity of ammonia release. And this is MESD contribution to the industry in terms of ammonia. And we make several publications. The recent 2 publications you can download for free from our website. And of course, we are keeping developing new technologies, trying to get new funding for our upcoming studies, which is here. In fact, by the 1st of this month, we have already started our work, starting to review all the technologies to mitigate ammonia release. And of course, we're also trying to work out all the practical scenarios which we can work with together with A-STAR, IHPC, later my colleague will present here, and TMSI, which will work on the environmental impact of ammonia release in Singapore. And please do feel free to approach us by visiting our website or contact us by email for any future R&D projects. Thank you.